Hello and welcome to this video on the Solow-Swan model. Today we're going to be simulating the Solow-Swan model with technological progress and population growth. If you've never heard of this model before, it's a good idea to check out some other videos on that first before coming to this, because I will be assuming that you already know what the Solow-Swan model looks like, and we're going to be focusing more on the simulation itself. We'll be simulating the model using R today. But first, we'll go into a very quick overview of the model setup. As in the standard Solow-Swan model, we have a production function based on a Cobb-Douglas production function here. Specifically, we have our output Y is given by our capital K, and in labor augmented technology A times labor. And then, of course, we have our capital to the alpha and our labor augmenting technology times labor to the 1 minus alpha. We have a capital accumulation process in discrete time where capital tomorrow is a function of capital today times 1 minus delta, where delta is our depreciation rate, plus the savings rate times today's output as well. So this follows a very clear intuition that capital tomorrow will be based on capital today with some level of depreciation plus whatever additional investment we give into capital for tomorrow. So our savings rate times our total income, or the output Y. Technological progress follows the structure that we see here, where technological progress tomorrow is given by today's technology times by 1 plus G, where G is the growth rate of our technology. This is just an exogenous growth rate. And population grows at an exogenous rate, where our labor force, or the population tomorrow, is given by 1 plus N times the labor force today. So then this means N is our population growth rate. Finally, we're going to define everything in terms of efficiency units. Now, efficiency units are basically where we divide all factors by this A times L. So efficiency units for capital are going to be denoted by this lowercase k tilde, which is equal to upper K on upper A, upper L. And output similarly is the lowercase y tilde, which is output divided by technology times labor. What we're going to do is, using the basic model setup, we can derive the steady state. Now, how do we do that? Firstly, we solve for k tilde and the change in k tilde over time. So this little dot here above the k tilde represents the change over time. And without going through the whole derivation, we can find that this change in the efficiency units of capital over time is equal to the savings rate times the efficiency units of capital to the alpha minus delta plus N plus G times K tilde. So what we actually see here is that on the left-hand side, this S times K tilde to the alpha is our actual investment level, whereas this right-hand side, the second term here, is the break-even investment required to keep capital stock, or inefficiency units, the same tomorrow. So then what we can derive from that is our balanced growth path, or the steady state. And this is just defined as where this k tilde dot equals 0. So what we do is that we put this left-hand side of the fundamental equation equal to 0, and we solve for k tilde, and we get our k tilde star, which is given by this formula here. S on delta plus N plus G, all to the 1 on 1 minus alpha. Now it can be a bit easier to understand this graphically. So on the right-hand side, we have a graph where we have our efficiency units of output on the y-axis and our efficiency units of capital on the x-axis. And this top curve is our production function So that's our output in terms of efficiency units. The curve below it is our savings function, right? So savings times capital. And the straight hand line that kind of looks like it's going at a 45-degree angle here, but it doesn't need to, is our break-even investment line. So that's this N plus G plus delta K. So this is the right-hand side of the fundamental equation that we see here. And if we start at any given capital level, so let's say this K tilde O here, we then can compare this savings curve to the break-even investment. And we see that when the savings curve is greater than the break-even investment, this left-hand side of the fundamental equation, or this SK tilde alpha, is going to be bigger than this break-even investment level, which means that capital stock tomorrow will be greater than it is today, which means the capital stock grows over time. And then in an iterative process, this will approach this level of K tilde star. By the reverse logic, if you start at here K0 dash, we're going to have a level where our break-even investment curve is going to be higher than our savings curve. In other words, the savings that we do, or the investment in capital stock, is going to be less than what is needed for the capital stock overall in efficiency units to remain constant, which means that tomorrow's capital level will be less than today's. And again, we have this similar movement back towards this K tilde star, technically never reaching this level, but coming very close to it. But of course, we can analytically derive, as we've done it at the base here, exactly what this K tilde star level is. So this is our steady state, or our balanced growth path. And given that this equilibrium is locally stable, in that on either side of that equilibrium, the dynamics tend towards that equilibrium, we're going to say that the economy in the long run will tend towards this steady state. And that's exactly what we're going to simulate today. When we are in this steady state process, we can look at the various different variables and see how they grow over time. So capital per unit of effective labor and output per unit of effective labor, our K tilde and Y tilde, are going to grow at rate 0. That's by definition. We set these equal to 0, and that allows us to then derive the growth rates of other variables. Our capital per worker and output per worker are going to constantly grow at this rate G. Again, G is the growth rate of technology. Our labor population by design is going to grow at the rate N. That's just the population growth rate. And then it means that our capital and output overall are going to grow at the rate G plus N. Now let's jump over to the simulation and see what this looks like in practice. Here I'm simulating this model using R, or RStudio specifically. And on the left-hand side here, we have our code. On the bottom here, we have our console. So you'll be able to see every time that I run a particular line of code, it will come up here in this console, give us some updates. In the top right-hand corner, we have the environment. So as we define every variable, they will appear here in this environment. And then any plots that we make will appear in the bottom right. So what we're going to do is firstly just clear our environment to make sure that we're ready to start from scratch. And today we're going to need 3 different packages. So the dplyr and tidyr packages are just going to help us to keep the code nice and clean. That's just my preferred style of coding. And then we're going to use ggplot2 for the visualizations that we're going to use. But let's get into the more nuts and bolts of the model itself. Here we have a Solow-Swan model with technological progress and population growth. And we're going to start by defining all of these exogenous parameters which we spoke about. Now, all these parameters here are just going to be defined based on what the standards are in economic literature. And so we're not going to do anything fancy here. This is not the point is not to play around with these parameters, but to just use some of the basic parameter values so we can understand the intuition. here, our alpha level, or the output elasticity of capital, is going to be about 30%. The delta, or the depreciation of capital, is going to be 5%. So that means our capital stock, which is existing already, is going to reduce in its value by 5% each period. The savings rate is 20%. So that means that individual households, they will consume 20% of their income, and then they'll consume 80% and they'll save the remaining 20%. The technological growth rate is going to be at 2%, and the population growth rate is going to be about 1%. Again, these are the standards from the literature and reflect approximately what we see in reality. Now, we have to define some initial values for the simulation to work, but it doesn't really matter what these are. So we're just going to arbitrarily define our initial capital stock and our initial labor stock as 100 each, and then we're going to define our initial technology level as 1. So let me just quickly run all of these, and you'll see as I'm running each of these lines of code, the values are popping up here in our environment on the top right hand side here. So exactly as we've defined them. The time horizon, again, it's going to be an arbitrary number, but around 150 time periods is a nice period of time for us to be able to see the dynamics of the model. Fantastic. Next thing that we have to do is we have to define some vectors, or basically these are just going to be placeholders to store our results. So big Y refers to aggregate output. And when I run that line of code, you see that it just generates this vector of 150 values. So from 1 to 150. And currently each of the values are just listed as 0. So it's just an empty vector at this stage. And I'm going to do the same for the capital stock, the labor force, the technology level, output per worker, capital per worker, and then output per unit of effective labor and capital per unit of effective labor. So now we just have a bunch of these vectors which are empty, going from 0 to 150. And then we're going to set some initial values as we did earlier. So we take these initial values of capital, labor, and technology, and we're going to put them in the first position in each of our vectors for capital, labor, and technology. Tuck, tuck, tuck. And you'll see that when I do that, for example, here on big A, the first element changed from a 0 to a 1, for big K from 0 to a 100, and likewise for labor. So next we get into the actual model itself. Now you can see here that this model is going to be performed as a loop. And what this loop does is it's going to go and time period by time period from 1 to 150 perform a number of calculations. The first thing it's going to do is calculate output, where our output, so our Y, is going to be given by our capital to the alpha times our technology level A times the labor force to the 1 minus alpha. Again, that's just our Cobb-Douglas production function. Next, it's going to calculate output per worker and per effective worker. And that's just going to take our output divided by labor at each time period. And then it's going to take our output divided by labor times technology. So A times L here. So these are just the definitions of output per worker and per effective worker. Next, we're going to calculate capital per worker and effective worker, and that's exactly the same process as we've done, except we have K divided by L here and K divided by A times L here. Finally, we bring in some of the dynamics. So for T less than capital T just means before the final time period, 150. K in period T plus 1 is going to be given by 1 minus delta times today's capital stock plus S times the output of this period. So again, this is just the formula which we looked at before for the change in capital stock over time. Similarly, we have the growth of the labor stock over time times 1 plus n, and the growth of the technology level 1 plus g. Now, let's run this loop here. Bang. And what you'll see when I run this loop from period 1 to 150, then all of these vectors start to change their values, and it performs the calculations, and then we have all of these individual vectors of all of our individual variables here with their defined outputs, defined levels. And now what we want to do is combine them in a nice table. So here I just combine them in the table, and then I've given some more intuitive labels to each of the variables. If I click on this, we can have a look exactly what our table looks like. Here we have the period 1 to 150, output starting at level 100, capital starting at level 100, growing over time, labor, technology, output per worker, etc., etc. But I think that this is a bit hard to look at, so we're going to plot this model out. Now, there's a few steps that we need to do just to manipulate the data to make it a little bit easier to plot. So I won't go through these in detail, but we're going to just make our results into a long table, and then I'm going to define what order I want the results to appear in, and then we will plot our model here. Okay, now this is where it gets a bit more interesting, because on the, if you look at these two top rows, we have capital and output. And then from left to right, we have the aggregate capital and output, and then per worker capital output, and then per effective worker capital and output. And what we see here is that, over time, we started at some arbitrary level of capital and output, and over time, these have both grown exponentially. Similarly, capital per worker and output per worker have grown exponentially, which is what we sort of see in practice in the world, at least since the Industrial Revolution times, that outputs and capitals in general have grown, and also per worker have grown. But then if we look at this capital per effective labor and output per effective labor, we see that while there's initial growth, at some point at this around 3.7 mark, the capital starts to taper out and reach the steady state. So this is what we saw in the graphs earlier, where we looked at this tendency towards the steady state. Similarly, we have output tending towards the steady state at a level of about 1.45 or a little bit higher. Again, our technology and labor on the bottom here are shown because these are growing at the predefined rates, N and G respectively. So what we want to do is we want to sort of characterize this steady state. And what we can do is actually calculate exactly the K tilde star and the Y tilde star using this formula that we saw before here on the bottom left here. So what we're going to do is just calculate exactly that, and that will give us our K tilde star level. And let's do the same for Y tilde star, which is just K tilde star to the alpha. And if we have a look at this K tilde star, it's 3.7024. So the theoretical steady state level is 3.70. And then we can look here on our graph and see, yes, actually the economy capital level per effective labor looks like it is tending towards that 3.7 mark. Y tilde star similarly is 1.48. And that's exactly what we see the output per effective labor tending towards 1.48 here. Okay, now what we're going to do is simulate some shocks. So specifically, we want to start by looking at a shock in the population growth rate. And we're going to let the economy continue at its steady state up until period 20. And then from period 20 onwards, we're going to say that the population growth rate increases 5 times. Now, I mean, the intuition is the same for any growth level in population, but here I chose 5 times just because you can see the dynamics a little bit more easily on the graphs. So let's start by initializing our model again. What we want to do is we're going to choose our K0, L0, and A0, so capital, labor, and technology levels in time 0, based on what we saw at the end of the previous simulation, right? So we want them to be around the level of the steady state. So I'm going to define each of those. And what this is doing is just taking the last variable, the last element of the vectors for capital, labor, and technology, and making them the first elements in the new in the new vectors that we're going to define. What I'm going to do now is just reset all of our vectors as well back to zeros. So again, we have each of them. For example, you can see y and y tilde here are just vectors of zeros, and then we will plug in those initial values. So for example, in the big A vector here, you can see the initial value is 19.1, and then it goes 0 onwards there. For capital, it's 31,000, and then 0 onwards. And for labor, it's 440, then 0 onwards. And then we're going to rerun this model. But one thing that we need to change is that the population growth rate is going to change halfway through. So we're going to say the population growth rate is 1% per time period, as we had previously. But that's just going to be our initial level. Here we're going to again loop over the same model. But if time t is equal to or greater than 20, greater than or equal to 20, we're going to be the population growth rate is 5 times that initial level of population growth. So let us run this model. Bang. And again, it's a bit hard to look at it as individual vectors. So we're going to combine the results in a table, and then the table's a bit hard to look at. So we're going to just manipulate our variables a little bit so that we can look at them in a graph. And voila, we see some of the dynamics look quite similar. For example, the aggregate capital and aggregate output, of course, labor and technology growth. But some key differences here. So firstly, in the labor, bottom left graph, we see that the curve of this graph is actually steeper than it was before. Of course, because we now have a labor growth rate that is 5 times what it was previously, at least from period T onwards, which is quite near the start of our modeling. Capital and output seem to sort of both go up in this exponential fashion as we saw before. But then we see here capital per output, and if you look very hard, output per worker, so capital per worker and output per worker have this slight dip that happens around the t equals 20 mark. And they don't increase as exponentially as they did before. They sort of slow down a bit, but then get back to this exponential growth. And it's the same for output, even though it's less pronounced. It becomes very clear when we look at capital per effective worker and output per effective worker, where for the first 20 periods, we're in the steady state, right? So the variables remain sort of flat, but then at the point where the population growth rate increases 5 times, we have this sudden drop off in the capital and output per effective worker, and then we have a tendency towards a new steady state. Now, this new steady state appears to be much lower than the old steady state, which is exactly what we would expect from the analytics of the model. So what do we say overall? Well, actually, to make this a little bit clearer, what I'm going to do is create some log variables. So to get rid of these exponential effects, so I'm going to create log output per worker and the log of capital per worker, and then going to manipulate them so we can put them in a graph. And here we see this log output and log capital per worker here. So initially the economy is tending on at its steady state growth rate, and then when the population growth rate increases, there's this negative level effect that occurs. It's more pronounced here on the capital side. We have this negative level effect. And while the growth rate of the economy appears to be the same as it was before, there's this kind of falling behind effect where the overall level is actually lower than it would have been previously. So you can sort of imagine the dotted line continuing here above and parallel to this solid line. Now this is what we call a negative level effect. Now we're going to look at a different sort of shock, and this shock is going to be a shock in technological growth. So here we're just going to start by resetting all of the vectors, putting them back to zeros as we did before. We're going to initialize these values for capital, labor, and technology. And again, because we changed that technology, the population growth rate, we're going to reset that to 1% per time period. But what we want to shock instead is the technology growth rate. So here, I'm going to set the growth rate to the initial 2%, which is what we had in the original model. But what's going to happen is that at time period t equals 20 and beyond that, the growth rate is going to be 5 times that initial level. So rather than being 2% per year, that'll be 10% per year. Okay, and let's just go ahead and loop through that model, combine our results, and let's plot that model as well. Now what we see here is, firstly, looking at this bottom left-hand graph, our labor, again, we go back to our original levels of this labor growth over time, but our technology growth over time here in the middle bottom panel is much faster than it was in our previous simulation. Of course, because we specifically induced this technological growth from time period 20 onwards. And what we see in our capital, our output, our capital per worker and output per worker, the exponential effects all look much stronger than they did before. So we see this exponential growth. The dynamics of capital per effective labor and output per effective labor look quite similar to the population stock, where we have a negative effect and then another tendency towards a new lower steady state. But let's have a look at the log of output and the output per worker and the log of capital per worker. So I'm just going to start by creating those variables and then rearranging them to be able to plot them. And what we see here is that when we look at the log output per worker, we were tending across along a steady state which had a slope that looked like this. But at exactly the point in time, t equals 20, where we changed the dynamics of technology, the slope of this graph changed. And then here we have a similar outcome with the log of capital per worker, although there's a little bit more of a gradual change. Here, a gradual bend in this, but we can see that from the comparison of the slope of this graph before the shock and after the shock, the slope is actually different. So rather than having a negative level effect, what we see here is a positive growth effect. So today we have looked at a simulation of the Solow-Swan model with technological progress and population growth. And we've seen that through a simulation, different kinds of shocks produce different effects. Specifically, we saw that a population change in the growth rate of the population led to a level effect, whilst a change in the growth rate of the economy led to a change in the growth. So a growth effect overall. I hope that you've learned something from this video, and I look forward to seeing you in the next one.